Let's look at twin primes. Recall that a prime number is a number greater than 1 whose only positive divisors are 1 and the number. So for example, the number 19 is prime because its only positive divisors are 1 and 19. But the number 35 is not prime because its positive divisors are 1, 5, 7, and 35. The primes are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, etc., etc. And here I list the primes up to 200. Notice that these primes start out close together, 2, 3, 5, 7, 11, but eventually become more sparse. In other words, the gaps between primes grow. Twin primes are primes that are 2 apart, like 3 and 5, 5 and 7, 11 and 13, 17 and 19, etc. The twin primes conjecture states there are infinitely many sets of twin primes. In other words, infinitely often, the gap between consecutive primes is 2. Now this seems to be true, but no one's been able to prove it, even though the conjecture is over 100 years old. And that's why we call it a conjecture, because it's not something that's been proved yet, it's just something that seems to be true. Mathematicians have made significant progress recently. In 2013, Yitang Zhang, a mathematics professor at the University of New Hampshire, proved that infinitely often the gap between consecutive primes is n, where n is some number less than 70 million. Since then, the 70 million has been reduced to 246. Now that may not impress you. You may think, oh, well, big deal. So the gap between consecutive primes is infinitely often n, where n is some number bigger than, smaller than 246. But actually, that is a significant advance over what we've known before. Now, if we can reduce that 246 to 2, then we'll have proved the twin primes conjecture. So far, we've discovered billions of twin primes. The largest known pair, discovered in 2011, has over 200,000 digits. 37568016955685 times 2 to the 66, 6669 minus 1, and plus 1. But we have not yet been able to prove that there are infinite many sets of twin primes.